Any preference for how I tell this story, Mike?
Start with the oscillators.
Start with the oscillators. All right, so in a dynamic system, the simplest system you could really have, if you want it to be a self-contained system, meaning not a bounded system by us or in an external environment always maintaining it or injecting it with energy, then the simplest thing you can construct would be a simple set of two oscillators, right? Why?
I don't know.
What if you started with one? If you start out with just something that's going around in a circle, and you were trying to define this as the simplest self-contained system, what's wrong with that sentence? When you look at the circle just going around, and I tell you it's a self-contained system, doesn't it seem that there's something missing? No?
That's why we're starting here.
Yeah, that's why we're starting here, okay. If you were to look at the circle, and then I were to ask you, is there any magic in this? The circle's being drawn by a thing that's moving around in a circle, right? You see in a point or vertex or something, but it's moving around in a circle, and you see a circle being drawn over and over on the board by itself. Would there be any magic in it? Would the explanation seem reasonable and sound already? Yeah, of course the circle's just moving around by itself with no reason. Like, this is where the mystery of gravity comes from, basically, right? Or an example of mystery of gravity, or electromagnetism. Anytime we see something moving in a sense that wasn't accounted for already, right, in intuition, you see it just moves in a circle, a straight line, there's nothing to act on, it just keeps going. But if it moves in a circle, now all of a sudden, you need to explain how it got that motion. How did it get its shape, right? Maybe if you just saw this going that way at some speed, and next time you look back, it was further down now, but still going the same speed. And that wouldn't be mysterious. You wouldn't need to come back and re-explain that every time you looked at it.
Circle needs another force.
It needs something else attached. There's a mystery inherent in the circle. If I told you it was a self-contained system, but it's just a point to do it in a circle, you're like, what's making it go in a circle? You haven't accounted for the circleness. There's obviously something else in the system, right?
Okay.
Now, so the minimum thing you could have in response to account for would just be another circle, like an inversion, but it's still a circle, okay? So two circles can create a closed, contained system, a manifold, a balanced system that uses its own boundaries on inversion on itself to maintain a shape, okay? Mobius connection. Why? Because the two circles are then going to complete the system. They invert on themselves, right? The whole inversion of the system goes back and forth with just two circles. You can't get that with one. With one, it's clear you at least have to explain what's tugging this thing in one direction over and over and over, right? Towards some central point. Everything we talk about in physics, everything that's in the field or domain of the conversation of physics, all the rules for how all the particles, every atom in the atomic periodic table of elements, how they all behave with each other, the domain of physics, all comes down to just particles having relationships, right? Things, in this sense, I mean particles meaning objects that have reliable, measurable properties every time we look, right? They have a certain amount of mass, they have a certain amount of charge, and those particles with those masses and charges always behave under a certain set of rules. They never disobey any of those rules. So these rules are set into the construction of reality in the simplest possible way you can have. A set of closed rules is two oscillators, two circles under connection. All right, the golden Easter egg that's widely known, I think, at this point in physics, the thing you would want to answer most, if you could, famously would be, what is the fine structure constant? This is the very famous outstanding question at the core of modern physics, the modern perspective we hold as a whole community of physicists. It's called quantum field theory. So the picture quantum field theory holds by Dirac is that there's a symmetry built into nature, geometrically binding all these rules together of physics. And one of the core geometric parameters of that symmetry is the fine structure constant. This is a dimensionless number in the exact same way as pi. It's a geometric number that needs to be known geometrically, and yet we don't have a story for why that value is the value that pops up. This is a measured number known in physics, right? Measured only. We don't have a story that gets us to it. We don't have a geometry that makes sense of this number. And yet, without this number, or if this number were different, the entire structure of chemistry would be wildly different or non-stable. This single number characterizes the structuring between the different atomic levels and orbitals and everything in all the chemical structure of matter. So it's very, very important in the current story we are using, but we're not deriving its value from our geometric understanding of quantum field theory. We're measuring the fine structure constant, what we see in the world, and getting that number to extreme precision, one of the most precise numbers we've got from measurement. But we don't know at all what the rest of the digits are, because we only know it from measurement. Okay? So, all of chemistry relies directly on this, and the rules of chemistry are physics. So physics is centrally bound up with the question of what is the fine structure constant. It doesn't get more central than that. It's like the primes in math. It's right at the root of everything. All right. Feynman famously noted that the fine structure constant we should be focusing on would be the square root of the one that we traditionally call the fine structure constant. That's I guess a small point, but it might spark a little bit of thought. Let's go into a simple explanation that gets us the fine structure constant. Now, I really want to preface that this has been a goal among physicists, a central goal among many physicists and among many enthusiasts that have spent their lives searching for ways to get to this number, to get to the geometric number that reproduces or matches, even without an explanation for why, just to get there. And the goal, of course, you can get there if you allow infinite complexity. We're looking for the least complex way there. That's what we've been impressed by. I want to start with the assumption that we just have our two simple oscillators, two circles that are connected under rotation and twist, and the domain of that entire action is maintained over and over and over under that two oscillating inverse actions. And I want to imagine that all of the actions that are important in this domain are widely separated in scale. So I can each time zoom out and imagine a whole different scale as I go out in perspective, allowing me to imagine that the domain of the intersection of the circles has at least a region that's much, much smaller than the external projection, okay, and making the external one spherical. So spherical, and the boundary of the action gets quieter and quieter and quieter as you go out, and eventually gets to a point where if you go any further, there's no more action. So it's a sphere minus its boundary, meaning all of its action is contained in the information of how the inside exchanges are going. Okay? So we have this simple shape whose on the inside being propelled by the action of a circle under Mobius construction, two circles under Mobius construction. Okay, so I want to start with some sort of volume then. It's being divided by a circle, and every time it does, it's 180 degrees from how it was. So I want to add a reflection. There's a reflection involved, and the volume divided by a circle. And this connection, these three things going on every time, back and forth, is equivalent to saying that we have a boundary from which everything on the inside gets twisted, but twisted another 90 degrees at the same time. So two 90-degree twists, and those two are both orthogonal. So I can characterize this algebraically or geometrically. Two orthogonal twists, and they're going to be within the boundary I'm going to call plane mass. You don't know the value of this yet. This should be the only unclear thing so far. I haven't written a number down for this. I really want to just sink in mind that there is a number, a geometric string of digits representing a geometric number, just like pi represented with the string of digits, built into geometry somehow that we don't know why geometrically, but it's also built into physics or the structure of reality so fundamentally that we're searching for its geometric actual explanation, right? I is the square root of -1. Make sure to find my terms in pi 3.14, the reference to relationship between the circle's circumference to its diameter and 1,000 other geometric references that define it. Really beautiful number. So this equation then, or this set of relationships that we're defining, we're just taking the geometry and saying, let's just imagine generally that the geometry is so simple and so beautiful that it's just a projection of some volume, some x cubed. This x is our thing that we're talking about, okay? We've got a volume that's being divided by a circle. We're just going to represent a circle geometrically as 2 pi, right? And we have the other conditions that we have a reflection happening every time this division goes on. So a reflection has the thing and it has the opposite of the thing. Okay?
Now, what the x and 1 over x are?
Yes. Yep. So we have, if you don't look at this part, the equation looks like you have something and its inverse, right? All right, now the combination of those rules are also equivalent to the combination of two internal rotations that are orthogonal to each other inside some limiting boundary. So this is the projection map, or this is the rotation map, or the set of algebraic relationships that our structure is just being set up with. So this is our simple start. We've got to give it a value for this. There's going to be some scale that we pick that's a limit. But this is all in reference to what ultimate scale? Doesn't there need to be an ultimate scale for a scale to even make sense? Right? This will be a scaled number. Some like 2.18 times 10 to the -8. It's got a scaling parameter here. But for any number to make sense, don't we have to define our universal scale, our 1? What does our 1 mean in this? Because so far it's an entirely geometric construction. It has pi, dimensionless. There's no dimensions on this at all, right? Until here. There's some scale. If it's a scale, and we're not even talking about any dimensions, if it's all a geometric relationship entirely, how could a scale pop up? Wouldn't there need to be a 1 for some actual unit for that scale to mean something? Yeah, right? Okay, that's what this system characterizes. The system we're calling the 1. Our geometry, we're going to call it our unit geometry. And it's under this geometric division. And when it's under that geometric division, a scale compared to the 1 to the projected point, the center of the outermost projection, or rotation or action. Does that make sense, or should I say that many times?
Say it many times.
So remember, our projection is a sphere at the outside. And the inside, it's got a circle or two circles under Mobius construction, right? So it's dividing if you look from the outside perspective, it's dividing it up this way and that way and this way and that way. It's breaking it up into pieces, okay? And under that projection, or that projection can be said as just being a volume under Mobius construction. So we add a reflection and the circle, it's a Mobius construction. So a volume under Mobius circle division is the same thing as just some boundary with which inside two rotations are having orthogonally. Okay? And this boundary is going to be some scale compared to the whole volume that's being projected out. So as we go out, it becomes more like a sphere and a sphere and a sphere, but quieter and quieter, and eventually limits out. There's the last action defining the radius of that sphere. There's a scale to it, okay? And that the center point to that whole scale, that projected balance point where the action seems most similar every direction you look, defines the one of our whole geometric balance. So the 2 pi and the i's and the scalene are all set in reference to that simplest projection. The whole system's self-talking, or yeah. How much did that follow? 10%?
Yeah, it's coming.
It's coming, okay.
That on the left, that defines Mobius, a circle under Mobius.
A volume, we're allowing all values in our x, right?
Yeah.
So a volume divided by a circle, but it's not just a circle. It's a circle that once you've gone around, it also has a whole 180 degrees backwards.
Yeah, and
Right.
is that what the one where x plus x is telling us?
Yes, this is something and its inverse.
Okay.
Yeah. So next time it goes back around, it comes back. So we have a reflection, and we have a volume under division of a circle at the same time. Put those together, and we have our really simple construction. I think the simplest you could define, it's another way of talking about it, it was 2 circles under intersection, right? And you haven't told what size the circle, so I'll allow all generalizations of it. Well, when you do that, you make it a Clifford Taurus. And if you want it to be an asymmetric Clifford Taurus, so you just put the restriction that one of the circles has to be much smaller than the other, then the asymmetric Clifford Taurus is now a square construction. It defines a manifold under square balance, right? Because if you cut a torus along its axes, you can unfold it to just a rectangle, right? So that's what I mean by square balance. It can be stretched into a square if you want. But there's one, so in that generalized construction you have, first of all, no, we go there yet. In the generalized construction we're allowing the circles to be a whole range of things, but one of them must be much smaller than the other. Then there's only one exact arrangement between circles that makes another square symmetry show up. Kind of vaguely getting where I'm going? There's a range of possible if you allow all Clifford Tauri. This is with the intersection relationship for a Clifford Taurus. And all of these are different dimensions. You can set them all independently. But it must hold that these two multiplied together equals those two. So as you set more and more, you restrict the others more and more. All right, so we're allowing all that generalization of Clifford Tauri. Among all the options then, there's only going to be one, since we're looking at asymmetric Clifford Taurus, one case in which these two are equal to each other. Right? There's only one place that can be equal to each other. Every other allowing makes them non-equal. And at that place, we then get another squaring. So we get a squaring here because we have a one case equal to another case, or we're making a squaring. We've got 2 independent cases. Here we have 2 independent cases, another equaling though. Okay, so we have another case in which the symmetry of the system becomes square. And this dual squareness under Mobius construction means that you cancel out. You literally, you back emptied the structure, or you refilled the boundary exactly opposite, just as a circle does if it's a Mobius circle. It now is back exactly backwards inside the circle that it used to be in, and then back to normal. Okay, so interestingly then, this structure, there's several ways we're going to be able to talk about the structure, of course. It depends on which features you're focusing on. Here we're talking about this external projective view in which everything looks three-dimensional around us. Okay, so it's like this giant sphere that we live in. And we're showing that the simplest geometry in which it was true we lived in a giant sphere that could projectively exist would be one that's just divided by a simple circle under reflection. So it's a Mobius circle. So it keeps doing it backwards and backwards and backwards, over and over. So that's one way of talking about our system. And when we talk about it this way, it's also equivalent to saying that there's two twists inside some boundary. So if you're external all the way outside this boundary, then the system is just a projective system. But inside the boundary, it becomes two orthogonal twists. So there's another limit inside in which those twists have finished. Okay, so this makes this equation really interesting to pick out a scale, because the scaling factor reminds you that all of it makes a unitary reference. Pi is always in reference to 1. There's a 1 floating around that we need to talk about. Okay? The 1 in a Mobius construction has very interesting properties, because the first thing to say about it, since we're under a Mobius circle construction, we're going to have a relationship that means you've gone 1/2 the way around in one way by the time you've gone 1 time around another. So we're building in a relationship between 1/2 and 1 fundamentally, algebraically. It's really simple things to code, but it's put in there, but at the same time, the same circle also has the condition you have to go around twice to go around once in another way. So there's a 1 to 2 relationship also built in. Okay? Two ways to look at the same system, two different things to point out about the same system. But those two things reference the system on different scales. It's a really important, subtle thing, that just referencing things on different scales can put you under a different relationship or different focus. In a sense, these are the same relationship too, but they're inverted. If we put this equation into Wolfram Alpha and check what is the condition that makes this true, for which x is this true? Are there any x that hold this condition? And it spits out 4 answers. It just tells you the value of these answers. I'm going to label them J1, J2, J3, and J4. So J1 and J2, we can draw a graph of where they are on the number line, basically. J1 is real close to 0, but not 0. So we've got a positive value on the x-axis, in the real number line. J2 has a more positive value. It's greater than pi. Pi is around here. J3 has a negative x value and a positive y value, or in the complex plane, we're negative in the real and positive in the imaginary. And J4, so I should be labeling them 1, 2, 3, and 4. So, really easily we can stare at this and notice if we're checking for symmetries, a real good thing to get in practice for. We can look for things that are balanced. What balanced symmetries can we pick up with our eye? Right away, you probably see that this looks like x3 or J3 and J4 are opposites of each other across that plane, right? Like a reflection. And they are, if I show you the numbers, they're exactly the same value in x, but they have opposite values with the same string of digits in the imaginary part. All right, these 4 values, these specific 4 points, represent the solutions to this equation, right? All of them at the same time are the solutions. Like when you have a square root of something, you can have more than one solution that at the same time is true. We have 4 solutions that are always true to this equation. But that's what they represent, the things that maintain this relationship, okay? They're literally the Lagrange points, the dead points, the central points of the rotations that are being put together to make this relationship. So we can check to see what kind of properties these zeros have, these roots of our equation have, okay? And let's do it over here. First thing to check, of course, is just what, if you think of it as vectors, and then add those vectors together, where do you end up? Okay, so let's just think of it as addition. So if we take J1 plus J2 plus J3 plus J4, you can see, add these two together, and their imaginary components go to 0, but their x components now, or their real part is way out here. But add those two together and it cancels. So the whole thing goes to 0. All right, so in a way you could think of these individually as the zeros of the systems, or the partition constants of the system. But in total together, they're at 0. This is a really nice balanced number we want to start with. Now let's check, consider their sum. What is their product? So we just multiply them together. And this time we get, think about this for a second. We said that the thing was a volume under division of a circle and reflection, right? What is then the product of all of the solutions of this equation? The product of, what do I want to call them? Its partition constants, or its roots. Take all of its roots and multiply them together, we get the circle. Now, interestingly, we can check for all kinds of other symmetries, but algebraically, we have a list of things we might immediately want to check. And the first thing, well then, if we get to 0 when we just simply add them, these things are all under square balance, because they're under our square symmetries of the two circles intersecting under Mobius construction. So let's take the squares and add those together. Right? That wouldn't take too long to figure it out as a fun question to ask. And I saw the answer before I really spent much time asking myself what it should be, and it shocked me. First of all, it was negative. Shocked me because of how beautiful and simple, and I should have thought it through before looking at it. But negative, first, why from negative? How could it be negative? We just squared all of the components. Think about it, some of them are complex, right? So we get negative inversions back and forth. We square them all, add them together, we get negative 4 pi. Now, in this thing, we started with a generalized volume. And let any root, we could extend anywhere for it to fit whatever it generally picked out. But here, by checking the roots and square them, we get to find its projection. We get to see the quadrants of the system. By quadrants is also the difference. It's defined, as the sum of the squares and the difference of the squares. And that one's, of course, 4 pi. So here we have a system whose quadrants, whose roots squared in sum or the difference of them is spherical in either case. And one's an exact inversion of the other. Beautiful. So I hope it's getting a lot more clear now. We didn't pick we asked basically what geometry is going to be maintaining this relationship. And now we're able to find from the roots verification of what the shape and structure of the geometry is. All right, here's the really interesting thing, if this wasn't already enough. Tying back to where we started our whole picture. Here we have the first component of this relationship, of this constructive division balance. Here again, the opposite of it. Well, if we take the first answer to this geometry, or this equation. So the first hyperbolic vortex partition constant, and square it, and that's equal to the fine structure constant. Completely equal to the fine structure constant. It's what it characterizes. And that makes this the second fine structure constant, and this the third fine structure constant, and the fourth fine structure constant. It comes with 4 kinds, and they're geometrically bound and defined in relationship with each other, but the relationship that they're characterizing is the simplest geometric projection that's available to geometry. The great sphere, minus its boundary, because it was quiet and boring on the outside, so a projective sphere whose action of interest is all happening on an internal exchange of boundaries that's just the simplest thing it could be, one circle and a reflection, or it's a circle under Mobius construction. Now, a circle under Mobius construction can be talked about this way or this way, so we could say it's also 2 circles and now can include the other phase, the other side, okay? This thing's also equivalent to saying that there's a maximum projected boundary from which all the twistings happening. So inside some boundaries where the twisting happens, and there's 2 twists orthogonal to each other of pi over 2 or 90 degrees inside some boundary, which introduces a universal scaling factor. So this is referencing, of course, to the projection itself, which is the 1. Perhaps arguably with 0, the most important numbers of all in all logic, right? And all mathematics. The big question in mathematics, as I understand it, is what is the field on which we are doing this arithmetic? Okay, and in all field theories, in all arenas of arithmetic, the giant question underneath it all is, well, what is the field that we're doing all this arithmetic on? What is this thing that all logic depends on? Here, we're talking about a geometric system that's the simplest one we can imagine. It's just a sphere, quiet and boring on the outside. And at some smaller scale, there becomes some interesting stuff going on, okay? But the projection point of the sphere, the domain that's all quiet and boring, it's just where everything exists. That thing itself is under division of this arrangement, okay? Or, as we said before, it's a sphere being divided just by a circle, okay, and a reflection. That construction could also be restated as 2 circles intersecting. Okay, the boundary itself defines 2 different circles intersecting under Mobius balance. They can maintain a Mobius construction. All right, a big step now to go for how does this number give us the structure in all of chemistry? What does the fine structure relate to that construction that has been made here? We can see that this structure has a scaling parameter. So we now have a domain, you can define it as the unitary projection. We have a scale that's important, smaller than the 1, okay? But there's an important scale in which something happens, and this characterizes that happening. All right. If there's an important scale, then it means we're not in a universe in which taking us all and shrinking us by 1,000, as long as we did our house and our planet 2 by 1,000, wouldn't make any difference at all. We're not in that world that we believe we're in. There are boundaries, they're just far from ours, so you would have to do many scales in order for it to show up until you got to something where it really did start to make a difference. We live in the scale of thought perhaps around when we perceive our world in the meter scale, some around smaller than meters or many meters, but that's the scale we're perceiving on. And down at 10 to the negative 8 meters, that scale in length is where the first boundary would show up in which things start taking on different actions in the projection. This takes away the black box of quantum mechanics. So Dirac gave us the Dirac equation and symmetrically coded what was going on. But what's missing, of course, from the Dirac equation is the parameters of the symmetry. So you have to put that all in ahead of time to find the symmetries and then try to code it. But it doesn't, when we found his equation, it's not like we could then say, oh, well now we can predict all those numbers. Okay, so we were still missing the understanding of why all of these things were in the shapes they were to begin with, or in the magnitudes they were to begin with. So here, we're getting a universal scaling, this idea that we could zoom out or zoom in forever and space would look the same, is being completely shattered here. We're saying if we zoom out from 10 to the 32, roughly 10 to the 32, we have our maximum scale of our sphere. All the way out on that scale to all the way down to close to 10 to the negative 8, things look like we think they are. You can zoom out and zoom in and it doesn't make much difference on how things are behaving. But once we cross this boundary, it completely changes. And then there's a 10 to the negative 18 in scale charge boundary where things are wildly changing compared to how they were changing here. Okay, and so on. Wait, I think, well, any questions about the fine structure constant before I move on?
Can you even go below that number there, that Planck number there, that scaling number?
The 10 to the negative 18?
Yes.
Keep going.
That is not the Planck mass?
This would be the Planck charge. This would be
How
the,
can
this
you
would be the
go
Planck
lower?
mass and the Planck charge.
Oh.
And then the next one, you can go lower, but you can't go lower in terms of mass. There will be no expression of mass lower than this. But you can go lower in a form, and the form you have available now is charge, and then length, and then time.
Yeah.
Right? But you can't measure with the larger measuring stick as you go down. Okay, so this one is 10 to the negative 35, and then 10 to the, I should probably put something between the projected one that we're in. 35, 10 to the negative 32, and negative 44.
What is that negative 44 then? That's charge?
There you go. So yes,
Smallest number.
this is charge. This is temperature. This is length. And this is time. So these are famously known as the limits, called Planck constants, right? The limits in physics, the mysterious limits of physics. I think they don't nearly get enough airtime. This is like one of the central mysteries of physics, known by every physicist. It's the central mystery, but almost universally just passed by. Like there's just nothing more we could probably ever say about this. Well, we should focus on its importance, at least. The fact that there are 5 implied limits to the dimensions of measure. First of all, the fact that there's only 5 dimensions of measure is really interesting, right? There's 5 ways in which we can independently make measurements of reality, and we can, infinitely explosive how we can combine all these. So it's combinatorially explosive, putting them together in many, many ways. But at minimum, the things by which you can make measure of would be a measurement of mass, how much mass something has, how much charge an electron has, how much temperature there is, how much length something has, or how much time it took between events. Everything else is a composite, a more rich measurement. The simplest things you could ever measure are those 5 things and those 5 things alone. The dimensions of physical measure in physics, by which we make story or mathematically map everything around us, right? All right, so the Planck length and the Planck time. Well, first I should say, how do we know those numbers are there? Like, how do we find those limits? We don't look around and see the limits. So these limits are implied from the measurements of the constants of nature. So we have 44 constants of nature. We make measurements for each of them. We've been getting better and better measurements over time. Scientists devote their lives to come up with ways to try to measure one constant of nature to just another power of one more significant digit. And that's making more and more precise measurements and focusing our vision of what reality is as they do. So these are really, really important, but we only know these numbers out to roughly 5, 6 significant digits. And then there's a lot of disagreement. The constants of nature, if you take them and then look at the units of each of them, like what measurement was being made, it was a measurement of seconds squared over kilograms, for example, right? You can have all kinds of combinations of the units, but those are the dimensions. Those dimensions tell you what the measurement was of kind, what kind of measurement was being made, and the number reports the magnitude of that measurement, right? So in each constant of nature, you can then look at the dimensions and look at other constants of nature, and then algebraically multiply these things together or square them, trying to cancel dimensions and minimize down to just the simplest expression of a dimension. So, like time equals the number you get when you take the constants of nature and you combine them, any constant of nature you want, you combine them so that you can cancel. You can pick ones that you can do it with, to try to cancel all the way down to just having just a time dimension left. Okay? If you play with the constants of nature and try to do that, you end up with this number. Then you can start from several different kinds of constants of nature to do this, okay? And it still happens. So there's some sort of limit. I'm going to try to do it without even writing the actual strings of digits. So there's a number for this. And the number has a scaled factor in seconds. That's the part I'm going to write down. Seconds. And there's a Planck length. And this one is in meters. Now, I really want to pause here for a second and make some emphasis on what I'm trying to say here. This dimension that we're using, the kind of representation for time, seconds, versus any other scaling factor you might want to use, is intrinsically important to the discussion and not a random happenstance of humanity that we ended up with that scaling. Okay? Most of these things started out with sloppy definitions, and we've gotten better and better and noticed connections and realized that the constants of nature and the equations of physics are telling us that there's a fixed arrangement between the dimensions themselves. And if we want to talk about the system in the simplest possible way, we should define the dimensions themselves that define the arrangements in physics. So the equations we write down, like F equals ma, doesn't have some weird number out here to skew it. It's just 1, okay? And we want all of our equations to just have 1. Now, if we want to change, we can skew our dimensions around. Let's go to feet instead of meters. And now none of them are going to work if there's a dimension of length in them. There's going to be a skewing factor. But if you use these dimensions specifically defined on these boundaries, then guess what? All of our equations work with 1s as their coefficients. So the dimensions we use, the coherent system of units used in science now, is not a hodgepodge collection of the happenstance dimensions we defined. That's how it started, and we've sharpened it and figured out relationships between them, redefined them because of that, and referenced them every equation we write. Okay? And since we're not putting coefficients in front of our equation term, we're saying this is the actual statement, not a version which is a coefficient in front, and we're referencing that there's an actual coherent system of units. Okay? It's a very important thing that I think is wholesale lost on people at this point. Well, I don't know. Well, I guess we'll find out. It's something to really make sure we're being clear on. That's what's being said here. That in physics, the relationships built in have boundaries called the Planck time, the Planck length. And the Planck time is the smallest resolvable discrete unit of time there is. It's the smallest resolvable discrete unit of anything there is. Okay? It's the smallest possible field of undulation back and forth. It's the smallest possible value or scaling there is. In the dimension, we're going to call seconds, which is really defined in reference to these boundaries or these relationships to begin with. The Planck length is defined in meters. Meters and the Planck length are defining each other in the same way that these things are defined off of the relationship between these. The speed of light is the Planck length divided by the Planck time gives you your Planck speed, if you want to call it that, right? Then you give your fundamental interactive speed, and that is equal to the speed of light. So this is how these things have their definitions today. And the meter and the second is commonly said to be defined in reference to the speed of light. Okay? But technically, they're defined in reference to all the construction in physics. And the rules, both algebraic rules and the system of the coherent system of units that we've adopted that explain those rules the simplest way. Okay, so there are 3 more. These are the smallest ones. And there's also the Planck charge. And that one represented in coulombs or Planck mass. And this is in kilograms. And then we have Planck temperature. And that's in degrees Kelvin. So these are 5 dimensions whose relationships are coded by physics. These are the 5 things you could set as your base, as the thing you compare everything else to. Maybe you like to think in terms of space. So this is the base you're stuck on. But you could switch it to that being the base. You could switch it to this being the base if you wanted, because these are all in relationship to each other under one simple balance. Maybe that's too fast, but let me make some space.
So, is it a question? If we take Planck length divided by Planck time, you can call Planck speed.
Planck speed.
Is it a boundary too?
Yes, it's a limit too.
So there are more than 5 boundaries.
Yeah, well, more than 5, but you have boundaries with single dimensions. There's only 5 of single dimension. All the rest of them are combinations of those. Yes, but yes. There's many more when you combine them from there.
And that limiting speed is the speed of light?
Yes,
The Planck length divided by time?
yes. The Planck length divided by the Planck time is the bounding speed, the Planck speed you could call it, and but it's called the speed of light. Yes. Fantastic, right? Because you're starting to see all the relationships built in. You could just, start from the boundaries and build them dimensionally. Yeah. And you end up with...
Is that how they got those lengths and time?
Yes.
They started with the speed of light?
Yes. They start with all the constants of nature and found when you combine them in a way that can cancel, every time you get one dimension to pop out, you know, you can cancel more, okay, now I have one dimension, it would be one of these 5. Yeah, so these boundaries are implied by measurements of the constants of nature. And the constants of nature explain the quantum field theory's parameters. The constants of nature are the parameters of the current story called quantum field theory. But they are measured, they're known for measurement only. They're not known from the theory itself. The theory codes very generally just its symmetry, its central symmetry exchange. Okay, it doesn't tell you the Scalene, or it doesn't give us a way right now to predict the actual values of all of its parameters. But when we put all these in, that symmetry exchange works fantastically. So it's very effective. Okay. Yes. So there. This is how we continue the discussion with quantum field theory, right? Talk about its parameters now that haven't been explained. And that just is a set of 44 constants of nature, or 17 mass assignments of the fundamental particles. So there's 17 different particles on the mass scale, 17 different things that matter, or scales of action under play, or 17 unique ones. But in general, the whole system, there's going to be a partitioning of exactly 44 different kinds of things, 44 different kinds of derangements. And why 44? Because we're starting with a system with 5 boundaries.
And 17 of those are mass of those 44 constants? Is that what you just said?
Yeah.
Of the fundamental particles.
There's 17 unique mass assignments.
And those define the fundamental particles.
Yes. Yes. All right, so when we have 5 boundaries and we have 5 actions, we're going to 5 anythings. If we take the derangements of 5, that's just always 44. It's just rule in math. It's just like if you want to build things from circles, you have the first scale is you have a circle. If the rule was we're building from circles. But the second scale is, so the next thing I can do to make us another sized circle would be just to surround it with, turns out it has to be exactly 6 to the next scale. So 6 circles fit around a circle in a plane, right? The same geometric construction we're basically talking about simply here is when you take any 5 things, you can break them up into arrangements that can derange 44 ways. So, 44 derangements of 5 whats? 5 dimensions, 5 geometric kinds of boundary that are all rotating against each other. Okay? That's the things we're talking about. We're talking about a projective system who defines the one that's under division balance. How one internally divides is the big mystery.
Well, derangement is not the same as multiplicity. Is that correct? How many different ways you can,
Like factorizations?
Yes.
No, it's not the same. It's related to, but you take all the factorizations and then say, but I want to restrict one more thing. I want that once you've factored them all, you've also closed the loop, so then you can just start the same actions in symmetry over and over and over. So if we start with a system, and I haven't told you what the system's composed of, except I told you that there's 5 parts in it, 5 moving parts in the system. Okay? Then you'll know, oh, that system fundamentally has 44 elemental derangements that would be interesting in it. No more or less, right? It's got 44. Okay. So we've got a 5-dimensional system, a projection, that we should talk a little bit more about, see if we can build a picture in your head. I inverted these, so this is the smallest one, and we got bigger and bigger as we go up. Except maybe you can see on this side here, let's block it. I have 10 to the positive 32 and 10 to the negative 32. This is the center of this one is where this 1 is. If you can kind of try to see the graph, let me just draw a graph. First thing to do is parse it to its inside and outside expressions. That's the best way to go. If we're going to have a balance, and now we want to talk more specifically about the geometry of our balance. What kind of shape is it tracing out? What kind of volume is at the bottom and so on? There's all kinds of details we can throw in. The most beautiful manifold of all, very famous of course, is the simplest double cover of the Cosine constant, or the simplest 3-manifold possible. So 3 things under action that can close a loop. If you put them on as a double cover, then once you close the loop once in one way, then you'll be under inversion, just like in Mobius connection, and then you have to do it again to get back to where you started. Okay, so the simplest possible double covered 3-manifold is called the hyperbolic figure 8 knot. And figure 8 knot. And I'll put up a picture on the video, but that's this shape we're talking about. And to be really clear each time, the strips are not part of the shape I'm talking about. We take those out so you can see inside for visualization sheets. You want to focus on the inside there. That's the part that really absorb. Right? There's a twisting, but the structure itself is knotted. There's a knot being maintained in the structure, in the shape. Okay? Now, when this boundary is formed, this is the boundary. If you fill in the strips, and you see, if you were to slide along the boundary, you're on the boundary, then you're dividing an outside from an inside. See, this boundary literally in volumes a fixed amount. Follow me? Okay. That is really interesting because you ask, what's the minimum possible geometric bounded volume? And since you have to answer that in terms of a closed manifold, it ends up being the simplest one that'll close on itself, the hyperbolic figure 8 knot. And there's a number like the number like pi again, but this number characterizes the volume of the hyperbolic figure 8 knot, known to be the minimal possible volume complement in geometry. Okay, so this is what we're going to use as our base structure for the way we're splitting our domain. We're getting really more specific now. And our division boundary itself, when we look at how it divides, is being internally divided into the hyperbolic figure 8 knot. Okay? I have to say internally because externally the whole thing looks very different.
Dad, when we think about this, do we think about a dynamic system, or is this just a fixed structure like a beach ball or something like that?
A dynamic system.
It is.
Absolutely.
Moving.
The system's, it's out there. Think of a medium of any sort, but if it allows waves, it's going to allow a distortion now that's spherical, but there's a limit. So let's start at the sphere's limit. If you're just 1 point past the limit, then things are entirely random and there's no sense of direction of anything happening. There's no field of any sort. No magnetic field, nothing happens to anything. Okay. If you come inside, you start getting some of that character where now there's a field. There's some action happening. It gets greater and greater as you get smaller and smaller scales. There's so many scales that you might not notice if you only explore a few of them. If you go all the way down to some scale though, that projection is being maintained by a twist and turn of some sort, a little thing that's doing something and continue to push things back out. And it folds on itself. So if it's a dynamic system, then we're going to want to ask, well, what's the smallest possible closed volume as the thing to rest on for our dynamics in geometry? We're asking geometers, what's the smallest possible geometry? And it's this one, the hyperbolic figure 8 knot. So that's the smallest internal construction, or what it looks like on the inside. And I have to say on the inside because remember when you're forming a manifold, and that's what the hyperbolic figure 8 knot famously is, right? The most beautiful one really. When you form a manifold, that means you've divided an inside from an outside. So you're in one or you're in the other, trying to make sense of what's going on. Okay? If you're inside that, then your universe has up to, or just has the volume of the hyperbolic figure 8 knot. That is your universe. If you're outside, then you're projected on top of a hole-shaped hyperbolic figure 8 knot hole shape, you would think, but it's also been twisted and turned under the Mobius constructions. So we got to get to what it looks like now. That sphere, I'm going to call the N hypersphere of maximal volume. It's a hypersphere. It allows you to extend the dimension you apply the rules to spheres to. So the hypersphere is put an X in for the dimension for the spherical relationships, and then you've got basically a hypersphere. The N hypersphere of maximal volume, it's the simplest possible shape on its outer scales, just the great sphere minus its boundary. So that's considered the simplest shape, just the great sphere. And the second simplest shape is the Clifford Taurus. And this thing is internally bounded by the Clifford Taurus. Okay? Meaning there's going to be a hole from the outside, a region, like we think of those black holes. There's a domain in which you're restricted past. You can't get into there. Okay? The shape of that hole is what we're talking about, because we want to know dynamically how does the hole maintain itself. And the hole, what we're seeing is the inverse rotated boundary of the hyperbolic figure 8 knot. Okay? But to us it doesn't look exactly like this. It looks like this that's rotated in two other ways in an inverse. And that forms the inside shape, the two circles of different scale that are sweeping around, and that's our hole. The hole for our simple projection has two circles in it that are sweeping around. So we have the simplest or smallest complement volume possible in geometry as our foundational shape, as the distortion we're requiring in the medium in order to get things going. But we're also noticing that the N the geometric shape known as the N hypersphere of maximal volume is the shape that's being formed on the outside of that projection. Okay, so we have these two beautiful shapes in geometry, the smallest volume complement and the maximal volume, available to geometry as shapes. Okay, what is the maximal volume about? That's the special dimension of this shape in which the volume peaks. So if you allow the dimensions just to slide up and keep checking this and plotting the actual volume of the hypersphere that it makes, then there's a specific number, it's not a whole number, in which the volume peaks and then turns back around. So this is the shape with the maximal possible volume available to geometry. There is a specific one. Really beautiful and simple, but the best part I think is that these two things are inversions of each other. The biggest volume possible, it rides on the smallest volume possible. Okay? And they're also very simply, they're defined as the simplest structures there are, right? The great sphere, and the second simplest structure is the Clifford Taurus. So in geometry or geometric algebra, these are basically the bounds of the simplest forms we've defined. So note that the 5 actions that go in around, remember, are all on different scales. So the Planck time and Planck length are the 2 actions going on inside the hyperbolic figure 8 knot. They're internally maintaining that construction over and over. That's what the 2 intersection of circles are on the inside. You can think of going around once the circle, the Mobius circle. When we go around once, that means we're on the inside. And there's 2 different circles. So the inside this is the inside expression of the inside circle, of the small circle. And this is the inside expression of the bigger circle. And both of these 2 circles come together to make the hyperbolic figure 8 knot. The outside expression of the Planck time, when you go around it twice, and now you've gone around once in another way, that way is the Planck charge, or bounds the Planck charge. It's the same boundary as this, except for it's the Mobius untwisted one, the twice as long one. Okay? And it's logarithmic, but it's still twice as long one. And same thing with this one. So this is the 1 time around the Mobius strip, and this is the 2 times around the Mobius strip. And that's the whole balance, except for the balance has a different geometry inside and outside, so there's an A scaling there. And we have that last twisting, the last action, the Planck temperature, which is crossing like all the way in intersection down here. It's being formed by the intersection between these 2 really strongly with the value around here, marking the limit of the temperature domain and the external opposite, its reach of projection. Okay, I hope some of that kind of puts some details in, but the biggest thing to keep in mind is when you're forming a manifold, you're forming an inside and an outside. The inside's made here from 2 different actions, the intersection of 2 circles. But we're only talking about the 1 time around the circle, that one being interacting. And then the 3 out here define the intersection of 2 circles. This one's how these 2 fit together. Defining the last external projection. So we're living in the temperature domain, which scales all the way from 10 to the negative 32 to 10 to the positive 32. Carving out the actual scaled structure of the whole projection. So the central point of that being 1, and all of these things then are dividing up internally the 1. All right, so we're talking about 2 oscillators. From the outside, it's 2 circles doing a thing under Mobius construction. And the inside is 2 circles actually constructed into the hyperbolic figure 8 knot, right? Really where was constants in nature. Yeah. So that means on the outside, remember the 2 circles are vastly different sized than each other. Well, that scaling, that difference, we should pay attention to. Every action on the outside should be balanced under this binomial factorization that respects that scaling difference. So we're going to have a primary action on a primary set of boundaries, and then this is the big scale, and then we're going to have a terminal action on a terminal set of boundaries, okay? But the terminal set of boundaries on the outside, there's no degree of freedom out there. They're the fixed ones, the bigger, fat, stubborn ones, and all the smaller ones are moving around them. This one is therefore a very fixed one in our equation. Our arrangement externally between 2 different circles is going to be just like this, where these things can vary, but this is always fixed. All right, why does this matter? Well, it helps us resolve It helps us resolve precisely what's going on in each one of the 44 derangements. So all the paths that you can take to get back to where you started in this construction that are available just from 5 base dimensions, we want to define them all now specifically. And we want to define them externally because we experience in the external world. So the external world has this exact construction maintained between its 2 circles. So if you want to address any constant of nature and see how it's expressed or where it comes from geometrically, you just reference it through this transform. I mean, you talk about it in this language. Okay, you look at, well, it's going to be something that's made up of a primary action on a primary set of boundaries. And here's the big first key. Primary set of boundaries is defined by the dimensions of the constant. So remember how the speed of light is in meters per second? So we're going to put in the boundary of meters, the boundary of length, which is the Planck length, and the boundary of seconds, so the boundary of times, Planck time. Okay? So boundary Planck length divided by the Planck time. And that's going to equal our primary boundary if the constant of nature we care about, or the speed of light. Because the speed of light is a constant referencing the relationship between these dimensions. It's literally what it is. Right? So we just put in the dimensions in terms of the boundaries of those dimensions that we have from our 5 Planck constants, and then we put it in our equation. I'm writing it like this because this applies to every constant of nature. This is how you find out what's geometrically going on with every constant of nature. So you just look at its dimensions, translate them into Planck values, or there could be mass of the electron if it was mass. In fact, let me write the list. You got Planck time if it's a time dimension. You got the Planck length if it's a space dimension. You got the Planck charge, or E, as another charge, electron charge, if it's a charge dimension. And if it's mass, you got the Planck mass of the electron, mass of the proton, and mass of the neutron. Okay, what did you say, Mike?
I'm asking if the Planck charge is the charge of the electron, are they equivalent?
They are almost equivalent, but there are 2 things you can put in this search. And when back to the temperature, just Planck temperature. So those are the boundaries you can search with to get all of the possible primary boundaries in your arrangement or in your translation of a constant of nature. All right. What's the difference between these 2? The electron charge is equal to the dimension, the boundary of charge itself, Planck charge, multiplied by the first hyperbolic vortex partition constant. So this is why Feynman, one of the reasons Feynman liked to say that this one, he didn't have this number, but that one's really the true fine structure constant.
Which is
Versus what we call now, it's the square of that is the fine structure constant. So this is, I mean, it's a small point. I don't really personally care as long as we can be clear about which one we're talking about. So we're going to stick with the way it's normally seen. I keep writing like this, but this is central to the charge of the electron, which is setting everything in chemistry. Right? So the electron's charge, or just the bound charge itself, can be the 2 options. And the difference between them is that. In the mass, we have 4 options, and temperature back to 1. Okay, the temperatures are projection. These are the things we're dividing up in its external domain. So this prescription works for all the constants of nature, all of them. Another thing to point out is that this constant boundary is equal to the Planck length times by the Planck mass divided by the Planck charge squared. I'm going to come back to that in a second. There's some more to say about it, but this is also numerically equal to 1 times 10 to the negative 7. Let's see, 0.1.
Help yourself if you want more.
That's what I mean, right?
Mm-hmm.
It's a 1. Wait, you got a 1 out of this and a scaling of 7. Remember where our 7 came from before, internally? 1 to 7, from the first scale to second scale. going from one circle to the big circle, right? Here, instead of getting a scaling that way, we have this inverse scaling, 10 to the negative 7, but in this power, in this logarithmic way. Very interesting, but it's the inverse symmetry, which hopefully triggers an idea that when you're scaling out in the picture in your mind of the boundaries of the shape, what it looks like inside and outside, there's a logarithmic scaling is the out way, right? The logarithmic is the out direction. Okay. So the numeric number here, why remember this? Why I care that it's shifted like this exactly 7? Besides the 1 itself, meaning that the rotation values of the length boundary and the mass boundary multiplied together equals the same number as the rotation of the charge boundary squared. Okay, so all these numbers are not 1s, and they cancel all the way out when you put them together. But the big thing is for here in a shortcut to memorize how to get good at calculating the constants of nature or checking or understanding what they're talking about. They're a binomial intersection of a big circle and a little circle of some kind, a closed path that's closing out one whole derangement. And the little one is always littler than the other one because of this. It's been multiplied by 10 to the negative 7. So whatever geometry you put in there, it's going to be shrunk by this guy. So that means when we're trying to calculate this, you can ignore this whole part at first and still expect an answer that's right after the first 7-ish significant digits. Maybe 6, right? But it's not, this doesn't come into play until the 7th digit. So you can ignore it and to check. This really, if you couldn't do that, you'd be stuck mathematically at this point, right? Okay, I know what to put in the boundary here, and I know my constant of nature value out here. But, then you just have to check this one. But, okay, that's not saying you can do that. If you thought these were all intimately connected and this wasn't scaled, you would be stuck and you wouldn't be able to apply it all to being responsible for it. Okay? So now we can check that value. And of course, in this case, the speed of light is 1. In several of them, it's 1. In several other ones, it's J1 or J1 squared. Okay, so the things that our solutions there tell you the partition story of what's happening, the boundaries that are intersecting, and then on the far side you can calculate, or just plug in Wolfram alpha, once you have this solution matching, and if it's a constant of nature that we know to enough significant digits, well, the more the better, the more the confidence, you can just check what the value for this needs to be. The value applied to the external arrangement of this construction. And remember how the Planck length and the Planck mass, I start from the bottom, Planck time, Planck length, and then we're on the outside, Planck charge, Planck mass. This is the 1 time around the circle, to which this is 2 times around, this boundary. Okay? Same thing with this one to this one. These are connected intimately. So when we look, we have now from the outside expression, the expression of 1 time around, the other expression also, divided by not the inside and outside expression, but from our outside point of view, we doubled up once. So we got an outside expression of the charge boundary. It shows up twice, right? So that's all we're saying here is that we let that one express itself both ways, and it's being folded against by this one, right? That's doubled. Both of them are external. So the external projection is held up by this, literally. All right. Any questions from here? Before I do, you want me to do numbers now? Or should I go into talking about what hyperbolic means?
Yes.
Hyperbolic?
So just in the constant there, action primary, action terminal, are these circles? Is that?
The combinations of these define one of the derangements. It could be a rotation around pi over 2 in this one action, and pi over 2 in a tiny action, and it can be all the way back around until you get there. But these are defining the derangements of the geometry of that's responsible for the derangements. That make sense? So yes, it's an action, but it's a specific action. It's going to tell you what the geometric action that it's doing. what boundaries it's intersecting, and if it's a 1, it's a 1-to-1 intersection. Right? If the coefficient is 1, then the whole story is just that boundary and that boundary are intersecting 1-to-1. But if there's a 2 pi out in front of it, now it's a different story. Right? If it's a 1/2 pi, it's a different story, and so on. So that's the best part about what I'm saying here. This algebra, extremely simple, is made even simpler by the fact that at first you don't even have to worry about everything in the parentheses, because it only comes into play at the 7th significant digit. So you just solve this first, expect an answer, check for an answer that makes sense, that's right to the first significant 6 or 7 significant digits. And the answer will be something geometric. That's the thing, and you can start interpreting what the action on the boundary is. If the action ended up being J1, like it is here, this is the action on the boundary for the electron, right? It's a geometric action, and now we know what the geometric action means, right? It's the first partition constant of that hyperbolic vortex arrangement, of that external sphere being projected out to a spherical boundary, but internally divided over and over on the intersection of 2 circles under Mobius construction. This was the aim of all the physics, to be able to have a way to make sense of the constants of nature. We have a simple prescription. This one right here, that when you plug in every constant of nature, putting the dimensions of the constant and translate it in terms of the limiting Planck constants, this set here, and find the geometric parameter that makes it true to the first 6 or 7 significant digits, then you can use that parameter to match up for all the rest of these and solve for the terminal constant. On the same construction over and over, you can decode the constants of nature, the central mysteries of our whole reality.
Just like you're talking about an equation to do all 44.
Planck's constant, the gravitational constant, the magnetic constant, the electric constant, all of them, all 44.
Okay.
You take those numbers and you translate them, just exactly what I said, put in this prescription. Take the dimensions, solve for that constant, which might be 1, it's 1 in several cases, right? And it's 2 pi, it's 1/pi, it's J1, it's J1 over pi. It uses basically just, these are just going to be made of pi and J1, and I think maybe Jr. Oh, that reminds me, I should say something about Jr real quick. But I'll just do that. J1 was right here, and J2 is around right here, and 3 right around there, and 4 around here. That's talking about so far when I didn't write the numbers down this time, but the numbers you could list in 2 ways. Or you could reference this thing in 2 sets of systems. You could talk about its x position and its y position, which is the way I've been talking about it, okay? But also you could talk about the radial distance from the center and the angle, right? In which case this number would be the same as before, this number would be the same as before, because their angle is 0, so there's 0 component there, but their magnitude and distance is the same on that from there. That's how they were defined before. But here we could also talk about from the center radius and angle, and define that point that way too, okay? And we find both of these ways useful for different systems we apply them to. So then there's a J_R and a J_theta also. They're not new entirely, they're new ways to talk about the system, like its radius and its angle, which might be the way you want to talk about it, but they're characterizing the same exact points, J3 and J4. Okay.
So that's a vector, or you could also think of it as a phase, couldn't you?
Yep, vector and phase. Yeah, really good way to translate it. So I bring that up because this Jr is going to be a coefficient in some of them, right? And it's certainly going to show up in the terminal one many times. That you can decode every concept of nature with this one simple pattern. It's a fantastically fun process finding that, discovering another 2 pi in nature, or knowing that you can tell the story of this constant's action by looking at its geometric relationship. That's an investigation I think everyone needs to spend some time on, I think. Okay, what does the division boundary outside the Planck mass look like? division boundary outside the plane mass? Well, it's an intersection of a tiny circle and a giant circle. Much more different than what I'm showing, okay? So the intersection is, this circle can sweep around, but because this circle is so small, it doesn't get to move around much. It's just it gets to sweep around, okay? So as it does, this is our construction. Well, now make this circle get bigger and bigger and bigger because I want it to be orders of magnitude bigger. And you can see the bigger circle makes it more like, you know, straighter and straighter. It gives us a very good cone. Why do we care? Because a lot of times in physics, we'll start with the geometric construction, since Einstein's day, that we're under the hyperbolic spacetime. This is our representation of hyperbolic spacetime. What do we mean by it? Well, it extends, I'm just cutting it off so that we can talk about its local character and shape and so on. It extends this way too. Okay, so the interesting thing first, remember, in order to have an arena of arithmetic, you need to have a field. I mean, you need to have exchanges that can be defined logically and they don't contradict, right? So our plus or minus or divide and multiply, they need to all be tied to something geometrically balanceable in the terms of manifold. This is the look at, when you zoom into it, this is what the manifold is looking like. It's the boundary that which doesn't get crossed. Just like the shape of this, the surface of this is the boundary that doesn't get crossed when this manifold is formed. Once it's formed, the inside is the inside and the outside stays the outside. There's no crossing anymore. Okay, same thing out here. The outside's manifold shape, it's bounded like this. Okay, it's got a cone, which might make really skinny, but still a cone in that. Well, this structure, no matter how we scale it, if we have the intersection of two cones, then there are a few things set. If we take a plane, and we want to slice, what I mean this way, our cone, so that we're perpendicular to the axis of the cone, then I'm always going to get a circle. I can get circles of any size in this construction. If we tilt our slice, so now instead of slicing like this, we go more like that, or more like this. Either way, we end up getting an oval. We get two centers. So it's like we started out with two circles, but now we're separating them. Okay? But we're also separating them in size. Let's make this a little bigger. Okay. If we're slicing here, something like that, we get a center here and a center there, say. What we're really representing is a relationship between two spheres now. Can you see two spheres in these cones? In this cone?
No.
There's, in this ellipse, if you drop, take the ellipse out and you drop in a sphere, and it's only this big, you go this high, it'll have a top point. You drop in a bigger sphere, you can keep going until you get one that barely touches the first point of the ellipse. And so there's a sphere underneath there. It will sit and touch that point. Okay? So one of the central, or the foci of the ellipse touches a sphere in the cone, the hyperbolic cone construction. And above, if you drop one in, its bottom point. So I really should put the points very close to each other because my ellipse wasn't very skewed. But that's the point. If you're dropping one above and below, so that the cutting plane is the ellipse, it's touching 2 points, one from above and one from below. Make sense?
Okay.
Okay. So in this construction, we immediately have ways to make relationships between two spheres of different sizes. We have a whole infinite range here, right? A large range at least. Okay, also, if we want to go further, we can get to the point where we're slicing this cone, where this is a limit, just like the circle is a limit to being perpendicular to the axis of the cone, it gives us a circle. If we're parallel to one of the boundaries, you get a parabola. This construction then, the hyperbolic four-dimensional balance of general relativity, has two really important limiting geometries in it. Has circles and parabolas. All circles, all parabolas characterize two different limits of this geometry. Okay, but circles and parabolas, interestingly, have universal parameters. Pi is the universal parameter for this circle. Pi is, when you know there's pi, you know you're referencing the circle. Just like when you know you have the universal parameter for parabolas, you're referencing parabolas. Okay, the circle, the circumference divided by its diameter equals pi. And the parabola has right to its focus, and the distance from here to here divided by the distance from here to here is always equal to pi. Oops. Here. Okay, so then we really care about them in geometry, of course. The central shapes we use in geometry. Right?
What is pub a number?
Pup's a number, like pi. Yep. So under that construction, we're saying now that outside Planck mass boundary, this is what holds. Okay? This is the division boundary maintained. You can scale it differently, but it maintains a structure that conforms to circles and parabolas being the bounded shapes. Now, what long distance force do we know that's confined to a parabola? Gravity, right? The fact that we get these parabolic arcs when we throw something up.
Oh, okay.
Right?
Yeah.
That's literally because we're interfacing at one limit, gravity limit, that's one limit. But that interface is this interface. It's following that boundary. I think it's really beautiful, actually.
So, can you get the gravitational constant out of this? If you
Mm-hmm.
Huh?
Mm-hmm. Oh, out of this?
Yes.
We got the gravitational constant out of the derangement it represents. So the gravitational constant involves more than one dimension. So it's not just a simple cycloid one, it's many parts. And we can go through the process of trying to show you how we would figure it out, right? I mentioned it a little bit before, but let's try one. We look up the gravitational constant online and find that its best known value is 6.67, 384, error of 80 in the 84, that's pretty bad error, times 10 to the negative 11. And then very importantly, we need to write down the units. And the units are meters cubed over second squared kilograms. All right, so that's where we're starting with. Now, we also starting with the knowledge of the value for the Planck time, the Planck length, the Planck charge, the Planck mass, Planck temperature. How would we translate this? The same way we translate everything. We get some primary reaction. This is some geometry story times y primary boundary. And we're going to ignore the other part because it's times 10 to the negative 7, and we don't care about that yet. We just want to get mostly right first, and then we'll worry about the smaller part. All right, so we know that the primary boundary has everything to do with that, right? Just the dimensions. So it's talking about the relationship, and this tells you the geometry of the relationship. The geometry of the relationship. What's the relationship? Well, tell me what dimensions we're using for our constant. So meters cubed is going to be Planck length cubed. That's easy. No real degrees of freedom there. Second squared, Planck time squared. kilograms, Planck mass. You might want to check Planck or the electron mass, proton mass, neutron mass because they were available. But up until then, there was no other options here. But it's Planck mass, okay? Now, you check that number, because you have the values of all the 5 Planck constants. So, we put this into our equation. We set it equal to this number, that number, right? And find out, and put an X, or put an A, put a variable there, so it'll tell you, okay, I know this was the input here, and I know the input over there, and I'll just solve for this one. Now, it might be 1 already, it could be pi, whatever. And let me see what we get. It's 1. Okay. So we find here that AP is equal to 1. So literally, the gravitational constant is talking about exactly the unitary relationship between 3 of these, 2 of those, and 1 of those. We're dividing these 3 by those 2. That's how we're putting them together. Okay? And it turns out, in order to go further in our full prescription now, was AP, which is 1, times BP, which is our LP cubed, over 2P squared MP. And then we just say 1 plus or minus. In this case, it's going to be minus. And we have to solve for the geometric action happening there. And we know it's going to be on our terminal arrangement of boundaries. Okay, all of them are. So at that point, you can now just go set it equal again to this number. Oh yeah, we're not going to have much significant digits on this one because look, 3, 4, 5, 6, and we've already got lots of error in the 5 and 6. So this was a little bit more advanced because I had to save it for the end to find out what had to be with confidence. But let me show you what it is. Minus pi over 2 times the gamma of 5 rotations is r squared. This is the gamma function, and my n should be a red n. N is equal to 5. And what 5? This is our fundamental 5 rotations of our system, the 5 bases or dimensions of the geometry, of the projected balance. Now, Cayley once said that all geometry is projective geometry. I think he was really onto it. He really was seeing what was going on.
Who said that?
Cayley. Oh, very famous geometer. The gravitational constant now, instead of being a string of digits, it doesn't really mean anything to anybody, now can be translated as, there's 2 things going on the big circle and little circle, right? The first thing is just an intersection. The first big circle is made up of just the intersection of the Planck length cube, or the minimal volume, divided by the Planck time squared and the Planck mass. Okay, so it's being divided up by those. And on the other side of things, we're activating the gamma function with all 5 rotations, so gamma of 5, in the radius of our division, the full reach of our division is radius squared, and a rotation of pi over 2. Kind of becomes very simply readable geometrically if you just know the algebraic pieces, right? If you just know what each one means. So start with the ones with the highest accuracies so that you'll be confident with your solution. This one, I had to infer a lot from the confidence of all the rest of the set. So the total derangements of the 5 boundaries, each boundary deranges into a whole number of things, right? The time boundary deranges into 44 things. And the space boundary deranges into 35 things, and the charge boundary deranges into 18 things, and the mass boundary deranges into 8 things, and the temperature boundary deranges into 32 things. The intersection of the charge, mass, and temperature boundaries derangements are the degree of freedom for chemistry, so we're going to fill out the whole periodic table of elements. Literally, those 3 degrees of freedom, as you add one more loop, go around the circle one more time in each of those 3 possible ways, you get to go in a different degree of freedom down the chart, across the chart, or a different category. Okay, E and log, which by me I mean natural log, because I know my audience likes that, are what? They are references to the trivial hyperbolic geometry. They're the hyperbolic numbers. How about that? But they're inversions of each other. They're functions that inverse functions that are defined as the hyperbolic functions. Let me explain exactly what I mean by that. Let me get some more board space for that. The simplest factorization infinite series would just be 1 over 0 factorial, which is, do you remember what 0 factorial is?
1?
1, yes. You didn't factor. You're still at 1. It's important to know. So 0 factorial, 0 factorization means you're still at 1, which means you started at 1. That's important. Plus 1 over 1 factorial, still 1, plus 1 over 2 factorial. Now it's 2, right? Plus 1 over 3 factorial. We keep going up and up. We're asking the simplest sequence of adding up all the inverse factorizations. Okay, well this gives us, since it's the simplest way to inverse factorize, gives us the coding for where the boundary for hyperbolic would be, meaning the one that reaches all the way out, the logarithmic or hyperbolic one, okay? And I can say this algebraically by saying this is equal to E, Euler's number. Fantastically beautiful insight, right? And that's why E is the hyperbolic number. And let me show you way more why. If you decide to get clever and say, hey, how about if I switch every other sign in this? Then what do we get? 1 over 0 factorial minus 1 over 1 factorial plus 1 over 2 factorial minus 1 over 3 factorial plus 1 over 4 factorial minus, and so on. All right, because this would be, you get to use every other one, like a Mobius strip. Remember, you go around once and every once makes a difference. And this one going around once, you got a different thing happening. You can have the 2 times around the circle or 1 times around the circle. But here, if you inverse every other one, so maybe you're still inverse factorizing, but you take the opposite sign of every other one, then it turns out that this has a relationship to that. It's its own inverse. It fully inversed by changing the sequence signs. Beautiful. There's a symmetry here that's really fundamental, but it's coding the structure of hyperbolic geometry richly.
So Euler discovered this?
Huh?
Did Euler discover that?
Euler discovered that, yes. If you never said whether or not who discovered it, you can assume it was Archimedes or Euler. If we generalize this equation, so our base representation for E, it's the sequence of inverse factorizations. It's an easy way to say what it is. But that factorizations allow the meaning to hyperbolic structure. And this is what I mean by that. If we generalize it, so take it to any factor, then it's now x to the 0 over 0 factorial plus x to the 1 over 1 factorial. And so on. Haven't really changed it much, of course, but it might be familiar. X to the 3 over 3 factorial, and so on. Well, if we pull this thing apart by its, I don't know, it seems one of the easiest ways to do it, but let's take all the even ones and let's take all the odd ones. If you take all the even ones, x to the 0 over 0 factorial plus x to the 2, Euler also discovered this, plus x to the 4 over 4 factorial. This equals the hyperbolic cosine function. It's half of its structure defines the hyperbolic cosine. If you take the odd ones, x to the 1 over 1 factorial plus x to the 3 over 3 factorial plus x to the 5 over 5 factorial, and so on, that equals the hyperbolic sine function. These are the definitions of them. So this structure of inverse factorization is intrinsically what we're talking about when we're talking about hyperbolic geometry. It's beautiful, beautiful things popping up. Now, if we take the same thing we did here, and we inverse our signs, every other one in both of these, we end up getting the the cosine function and the sine function.
If we do what?
If we, just like we did here, we decided that, okay, every other one of them make negative. If we do that here and here, then this turns into the cosine and sine functions.
But keeping the odd even in the denominator, right?
Yes, yes. Keep them separated by odd and even, but then also alternate every other sign, and now it goes into cosine and sine. All right, so E, we really care about now, right? It's the fundamental sequence for inverse factorizations, and if you want those factorizations to self-close, you would need a symmetry like this. Very interesting. You combine this and combine that, and you got your one. Okay, and a sequence of how they, at more finer and finer and finer action, behave. And we get our traditional cosine and sine functions popping up too. Well, why do I bring all this up or so much on hyperbolic? Because our construction is hyperbolic. At the core, it's based on the hyperbolic figure 8 knot. On the outside is the n hypersphere of maximal volume, whose internal boundary has to be explained as clearly as you possibly can, right? It's got those two different scaled circles, but the chiral action between their intersection is probably not as clear. It's the hyperbolic boundary that defines it. So the action from the inside to the outside of how we're connecting small circle and big circle is really the open question here. And I'm going to say that the primary action on that connection is always just the hyperbolic construction, literally the hyperbolic construction. And here's how I'm going to show it. In our Planck lengths, we had 5 rotations and 5 powers, or numbers of things that was being rotated for each. And Planck time had rotation 0, and it had derangement 0, which was 44 in the Planck length. Rotation 1, derangement 1, which was 35. The Planck charge had rotation 2, and derangement 2 and Planck mass, and Planck temperature, and the derangements of 4. So these 2 parts each define each of those boundaries. If we take them apart and ask, what's basically the whole matched sum of these things? The whole set, not just the derangements and just or not just an individual pair, but if we want to get the whole set at once, what do we have? Well, we can take the sum of all of the derangements. So where k is equal to 0 through 4, all of them added together. And we divide that by the product of all of the rotations, where k equals 0 through 4. So we multiply all of these together. And then this is equal to, like in every case externally, the binomial factorized union of something up front times by 1 plus or minus something on the back end, right? This construction is going to be the same thing. But what happens here is that whole set, when we take the boundaries themselves and try to ask, we're intersecting them all the derangements divided by the product of all the rotations, we just get the elementary inverse factorization sequence. Really well. The whole thing is just under the hyperbolic balance. Okay, and externally, the gamma function, there's an argument in here I'll get to later, but right now I really want to harp on just this. On the one side, it's just maintained by the hyperbolic factorization trivial sequence. The whole hyperbolic construction, all the rules implied. On the other circle, it's the gamma function. The gamma function can be pulled apart into 2 internal, 2-dimensional functions. And the P. The Q regularized gamma function and P regularized gamma function. When you add them together directly, you get one. Q of A and S, so it's a 2-dimensional argument. When we pull it apart, it has to be P of A and S equals 1. But if I take the derivative P of ANS, I get 0. Or if I put in 1 and leave this generalized, in both cases, e to the negative x, and 1 minus e to the negative x. Okay.
What are big Q and big D?
These are the Q regularized gamma functions. So these are, the gamma function pulls apart into these.
I see.
And when you put in 1 and x as your parameters, so you're addressing it to just a unitary condition and say, what is it? Well, what we're doing now is we're doing e to the negative x. And when you're doing, in the other one, you're doing 1 minus, the reflection of it. So the difference between. So this, I'm relating them now, I'm hoping your mind jumps to say, hey, this is very similar to that, right? E to the minus x compared to e to the x, which means what we're doing is we're talking about a system that pulls apart in inversion of e to the x and reflected inversion of e to the x on the other side. It's e on this side, and it's the opposite of e and the reflection, right? It's really, really intrinsic. So the gamma function is the hyperbolic factorization function. It's how things hyperbolically factor. That's what it's talking about directly, right? Because this is the hyperbolic factorization parameter. If you've got e, then, and it works for any x, it fundamentally maintains the hyperbolic boundary. So our Mobius simplest construction, or honestly, the simplest geometry I can visualize, right? Just a sphere that's projected up on something. The simplest boundary you can define for it, responsible for the projection. So some internal boundary has to have some shape. The simplest shape you can define is, since the sphere itself was already taken as a shape, the second simplest possible shape in geometry or algebra, the Clifford Taurus. And we're going to restrict it to ones that are asymmetric, so one of the circles involved is much smaller than the other. And we end up getting that the whole structure is under hyperbolic balance, and it splits to the outside domain to being hyperbolically balanced and doing these inverse hyperbolic actions, which requires going around and cycling in a Mobius way. Okay? Fantastic. Really, really, really fantastic. Yeah. So the next step is, of course, to extend this whole thing into chemistry, but I'm still preparing all that. And that's it for now.